Really?
Okay, so we're going to talk about the error in using our Taylor polynomials to approximate our functions. Okay? So if we take a function and we write a Taylor polynomial and we center it somewhere, let's call it C. Okay? If we move away from C, how off are we going to be for if we were to actually plug into the real function? Okay? That's what we're going to talk about. And we have what's called the Lagrange error bound.
Is there an alternative name for that?
Oh, yeah, there's somebody who invented it first but didn't get credit.
Lagrange.
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 It is the Lagrange. The amount of lag.
Okay. So there's a couple different ways that we can write it, okay? First of all, we have a remainder. If we take the function value and we look at how it differs from the polynomial value, there's going to be what we call a remainder, whether it's a little bit more or a little bit less, right? We don't really care if it's positive or negative. We just care that's a little bit off, okay? So what this says is that our remainder, and maybe I should zoom this in a little bit. I know it's in front of you, but our remainder looks like this. Okay, does this look familiar?
No.
No?
I don't
Like-
know what this is.
Yeah, it does.
Okay, don't worry about the z. But the pattern of derivative over factorial
Yeah. It's just
times x minus c to the same power. Notice how these are the same power, right?
Wait.
Okay,
That's what we did yesterday.
yes.
Plus the
That
Z
says
in
f of n plus 1, not f prime of n plus
Remember our conversation yesterday?
1. I thought you said that was the derivative, though.
Yes, once you get to a certain point, your derivative gets
Oh,
in
never
little-
mind. Okay.
Okay.
I thought that was saying you're plugging in n plus 1.
I couldn't do n plus 1 tick marks.
I get what no.
Okay.
I get it. Sure.
So here we go. Here is our function. Nope, here's our function. It is the polynomial, so our Taylor polynomial plus some remainder. Okay, we're good there. Now our remainder is always going to have this form. Now, what the heck is that z? That is bothering you. Okay? What this is, it's the max on the interval. Okay? So whatever interval we're talking about, and by interval I mean we've centered at a number and we're using a different number to approximate it, boom, there's your interval. Okay? Whatever the max derivative would be, that's the number you're going to plug in there. So this is going to be a numeric value. If you wrote a 5th degree polynomial, your remainder is going to be 6th derivative over 6 factorial x minus c to the 6th. If you have an 8th degree polynomial, you're going to use 9s for all of those, for that term. Okay? So it is similar to in the fact that with our alternating series remainder, we talked about the next unused term for our alternating series. You remember that? Okay. This is still the next unused term. The only difference is we have to think about what the derivative would be, what the maximum of it would be on the interval that we're looking at.
And that's our error? It's just the maximum?
That's our error is this whole thing. Max derivative over factorial times x minus c to the n plus 1. Okay? Now, what numbers are you going to know? You're going to have to do a little bit of work, but you're going to be able to know this number right here. Obviously, you're going to know this number right here. X is where we were centered at. Nope, sorry. C for center. C is where we were centered at. So that's either not going to be there because we centered at 0, or it's going to be, if we're centered at 2, that's a 2. Well, then what are we plugging in for x? X is wherever we're approximating at. So if you've centered it at 0, but we're going to approximate at 1/2, that's what would go there. Okay? If we've centered at 3, but we're going to approximate at 2, that's what would go there. Okay? Just for you, Richard, here's a little history about our mathematician. Okay.
Joseph.
Is it Louis or Louis or Louis? Louis? Joseph Louis?
JLS.
Oh, we're not gonna go through it.
Just skip it.
For later. Okay, so go ahead and get your calculator out because we're going to need it.
Ooh. This means calculator on the test.
Yeah.
Yeah, definitely look like this.
Also, I don't know if you've even looked at your gold sheet. Nobody has been complaining, so I assume that you weren't looking at it. I scheduled a quiz for Tuesday.
When will we come back?
Hold on.
I bumped it to Wednesday. I wanted to make you aware.
Is that for sure, or is that?
No, she's gonna
Maybe
change it
you
up
are.
on us.
She's gonna email us halfway through the weekend. By the way, it's Tuesday again.
First of all,
She's gonna
we
go
are
off on us
making
now.
things up
Yeah, but only
about
if we can find out.
what actually happened last time.
Because Richard was responsive.
Okay, let f be a function with 5 derivatives on the interval 2 to 3. Oh, look at this. The fifth derivative of x is always less than 0.2. The fourth degree Taylor polynomial for f is centered at c, is going to be used to approximate f of 3. Okay, so first of all,
That's a lot of words.
I know.
What?
We have a Taylor polynomial centered at c equals 2. Okay. What?
He's
circling it.
Okay. But we're using it to approximate f of 3. So the difference between our function value at 3 and our polynomial of 3 is going to be our remainder at 3. Now, we have a 4th degree polynomial that we were working with. Okay? So our remainder, if we have a 4th degree polynomial, what factorial and exponent are we working with? What's the next
4.
unused term?
5.
5. Okay? So we are talking about the maximum of the 5th derivative over 5 factorial times x minus 2 to the 5th power.
I just wrote if.
Yeah.
Whoops.
Oh, well, that's fine. It's an absolute value, though. Okay, why did I write x minus 2 to the 5th?
So wasn't that
C is 2.
Okay, we centered at 2. Okay? But what should really go in for x?
I don't know. 2, 3.
We are approximating f of 3. So x gets replaced with 3.
What did you say?
1. I just goes away.
What?
Just goes away.
Well, I mean, it's 1 to the 5th, yes. All right? And what do we know about our max 5th derivative?
0 is
Less than 0.2.
Okay, we have this right here. So we can say that our error is going to be less than 0.2 over 5 factorial times what's now 1 to the 5th.
Why didn't they just give us the exact value of that 5?
We don't always know.
But they know
We're
somehow that
because we're approximating. We're on the interval 2 to 3. We don't know what the derivative would be because we're not centered at 3. We're centered at 2. So we have to think about the function's max derivative there, so that we can figure out what the polynomial would be written as. Okay. All right, calculators.
like,
What is this?
oh, it's
0.2.
1 over 600.
1 over 600.
Yeah.
Okay, for this example, I'm going to go ahead and round it to decimal places. 1 over 600 is perfect. But I see in part B, I'm going to be working with this right here. Okay, a decimal. Okay. Now, let's say, like you did in 41, we plugged 3 in to our polynomial, and we got this number. Okay? Well, we're saying that that approximation only differs by the real value by 0.002. So if I'm talking about the real f of 3, it would have to live in the interval 1.763 minus 0.002 and 1.763 plus 0.002. This is like belongs to it.
That's currency.
Like it belongs.
That's a symbol.
Is it just
What?
a C with a line in it?
Kind of. Unless you want to write it all out in words. F of 3 belongs to the interval. Okay, this is a different shortcut.
I've never heard of that before.
Yep.
Just write it as inequality.
Yeah, that would be fine. Okay. So we have 1.761 and 1.765. We know the real f of 3 would be in that interval. If you write it in as an inequality, that's fine too. Okay? So, part C, could f of 3 be 1.778?
No.
No, because that number isn't in this interval we just created. Could f of 3 be 1.764?
No.
Yes.
No, yes.
We didn't explain why.
Can we just point upwards to the section B?
Zane.
Not in
Alright, who did? That's right.
not too bad.
Okay. Well, that was kind of boring. I mean, we didn't really have to do a whole lot of thinking about like the max derivative or anything like that. Yes.
Well, that doesn't really matter.
Uh-oh.
Oh yeah, why is it inclusive?
Well, yeah, because technically we have this right here. We could probably make them parentheses and be okay. Yeah. I would agree with you on that. Now, when we talk about, in this case, we can use a less than sign. But when we have problems that don't actually give us this right here, you would probably want to use less than or equal to because we don't know which part of the derivative we've been working with. Okay. So there will be, most cases you will have that equality in there. All right. Come on. I've been like avoiding restarting my computer all week.
Uh-oh.
Why don't you just restart it? It takes like maybe 5 minutes.
I understand that. But I also have like a lot of things that I'm working on and I'm not ready to like.
Don't ever let Caleb touch your computer.
That was your fault.
Okay, read
Push the
through
button.
example 2.
That was funny though. That was you gotta
So,
admit that was
like,
funny.
Stop on
You
it.
should
What if you
change
just
your
leave your
username.
computer and that comes out? Then you'll lose those files anyway.
That's
What?
true.
Well, it won't because I'm not there to say like, because if it tries to restart, it'll say, do you want to save this? Do you want to say this, you would
Yeah.
say this.
It'll like force it. Well,
Why don't
Read
you
their
say-
read their example too. Don't worry about my computer.
Well, no, actually, it's the word so
Yes.
we have to know those guys.
Yes. So find the fifth degree Maclaurin polynomial for sine of x. Where does that mean it's centered at? Okay, please take the next 2 minutes
So C is 0.
to write the fifth degree Maclaurin polynomial for sine of x. Really you need to worry about like the number of terms isn't always the same as the degree. All I want is the polynomial. Don't worry about the error yet. I just want the polynomial. So I'm just asking you to do what you did in your assignment yesterday. Find the polynomial.
They're not there.
Oh, fifth degree, not fifth
All right, Chris, what do you have?
I have x minus 1 over 2 factorial x cubed plus 1 over 5 factorial x to the third.
Thank you. I've been forgetting to write this. Kind of an important thing. Okay. Do you agree with what Chris has?
Yes.
Thank you, Chris. Okay. So now, use your polynomial to approximate sine of 1. So, sine of 1 is approximately our polynomial. Well, our function is sine of x. So sine of 1 means we're just plugging 1 in. So let's use our polynomial to approximate it.
I don't table number. I just keep it only on roughly
Okay, this isn't that bad. What's this fraction? Something over 120. We'll start there.
Isn't it 41?
That's 20 over 1.
Well, it's 5/6 plus 1 over 120.
20 over 1.
Does 6 ever? Does
Oh,
it
no,
count
yeah,
negative
yeah,
numbers?
19.
1 over 100.
141.
Oh, no.
But yeah,
Yeah,
negative 19.
that's what I said.
101 over 120.
I feel like that was really painful for you. Like you're just listening
Well,
to
we
it
were trying to
and
do
you're just
mental
like,
math.
I'm waiting for the right number.
That is really like a prime calculator though.
Still have
Yeah, when your calculator does fractions.
Okay, so
There's
I-
parentheses in the division sign.
Alright, moving on.
Now, I want to know the maximum error in your approximation. Okay? So if you notice, I went all the way to the sixth derivative.
What?
Why?
Nobody asked for it.
Why do I need the sixth derivative?
Oh, because you have to
Error
use that
For
for
the
the
error. So our remainder, which is going to be our error, approximating at 1, is going to be the max
It's
sixth
always like this.
derivative.
It really does.
You can say that every time.
Okay, hold on.
Of Z.
So the sixth derivative max over 6 factorial
X is
times x minus 0 to the 6th. X is where we're approximating. 0 is where we are centered. Just focus, please. Our max derivative, Caleb,
Yes.
negative sign of x. What is the biggest y value we could have?
Am I supposed to know that? How do you know that?
You
I
know
would
what
do.
that x looks like?
Like, isn't
The
that
biggest
what-
y value, negative or positive?
I don't know. +1?
Oh, positive 1 and all the way down to negative 1.
Does it have to be on the interval?
So here's the deal. On the interval,
Oh, okay.
on our interval, we may be overshooting it just a little bit. But anytime we are working with sine or cosine, and it oscillates between two values, just use the amplitude so that you don't have to make any further calculations. Okay? We'll just make it easier on ourselves. Yes, we might be overshooting it by a little bit, but that's okay.
So it's 1 over.
Okay? So the amplitude is 1. So we're going to use our max derivative as 1. Okay, so our error is
Why is it now less than or equal to? The other one was less than.
well, because they actually gave us that inequality. This one we don't know if it's equal or not. So I'm just going to say that that's a possibility.
Why is it called R?
Because it's the remainder, and remainder starts with R.
Okay.
Okay.
So we have to use R. Like it can't just be like error. Like
If you write error equals, I'm not going to throw it in.
Okay.
Okay. So this approximation right here is only off by at most 1 over 720.
That's pretty small.
And
Yes.
720? Is that just the
6 factorial. Okay. So
I'm still a little bit confused on what the Z is.
It's just the max.
we don't know what number would give us the biggest derivative in that interval,
Yeah.
so they can't call it x. So z is just a random letter signifying that you need to think about where you would be biggest on the interval for that derivative. With me? All right. So the sine of 1 is really between, help me out, take 101 over 120 and add 1 over 720.
Oh my goodness.
I'll let you use your calculator and give me a decimal to 5 places.
What mode do we have to do? Why 5?
Just because it's such a small number. I know that we like 3 decimal places, but I kind of like Where?
At the very top.
Yeah, this is 3.
Gives 3 decimal places.
Fine, give me 3 decimal places. Point 843. And on the low end, 0.84.
1 and 0.
Because our remainder was what? 0.001. It's pretty cool.
Pretty small.
Okay. So could the sine of 1 equal 0.9?
Nope. Too
No.
big.
Do you see how this could have been helpful before the time of calculators?
Yeah.
But now we have calculators, so
Agreed.
it doesn't really matter anymore.
So how come we don't learn this first?
Learn what first?
This.
Before what?
Before we learn how to use our calculators.
Ha.
Well, when you said
Okay.
you could rejected that idea.
After row 1. This.
Oh, why isn't it not
Algebra
You
one
need a
derivatives.
working? Because I need to restart things.
Yeah. There's functions you won't know until 3 years from now. Here's the derivatives of
Which is something you also.
Wait, there's a college.
Isn't there?
Oh my gosh.
Oh, I was like, did I copy it wrong? Okay.
There's no back on mine.
Sorry. Write the fourth degree Maclaurin polynomial for e to the x.
Can I just say they're all e to the x and stuff? They're all the same value.
Okay. Are all of our derivatives e to the x?
Yep.
Okay. So e to the x is approximately our polynomial 1 plus 1x plus
Writing 1x. Some kind of fulfillment.
what degree? Fourth?
Okay.
Cool.
Cool.
Cool people rate
It's true.
And zero.
Yeah.
We then want to approximate e.
Yep.
Okay. That's e to the first power, right?
Mhm.
So what are we plugging in?
1.
We're plugging in 1. So e is approximately our polynomial at 1, which is 1 plus 1 plus 1/2 plus 1/6 plus 1/24. This is a non-calculator problem, ladies and gentlemen.
How am I supposed to add this?
Wait.
Making common denominators is really difficult in this case. I mean, we're really going to have to think about it. What's our common denominator?
It's
24.
That was a big sarcasm. We have 24 over 24 plus 24 over 24. Okay?
That gets you
I
48.
got that much.
Okay, 48 over 24. Okay,
So 17 over 24.
No, it's 60.
so this is 12 over 24, right?
Yeah.
4 over 24.
Gosh.
And 1 over
16
Five.
64 over 65.
65.
1.7. What happened if you tried to do negative 1 factorial?
Your calculator will give you
Does it only work for positive?
whole, it only works for the whole numbers.
Arrows and that.
0.
What about the integral definition of factorial? Would that just like break down into like the integral definition of factorial for like fractional numbers and all that jazz? Does that like break down and not work on it?
Now it's for the next part.
Like I'm just curious to hear.
Right.
E6.
Let me get through this first.
Okay.
Okay. All right.
E6.
Here's our approximation.
Yep.
What's the error bound? How much does this differ by the actual e to the first power?
Wow.
So our remainder
Yep.
at 1 is going to be our max fifth derivative on the interval divided by 5 factorial times 1 minus 0 to the fifth. Okay? What's our fifth derivative? E to the x. And our interval is 0 to 1.
So the
Okay.
max value is
It gets bigger.
So should we just call it 3?
So our max value is technically E, right? But we're
Finding E.
okay. So what is E close to?
2, 3.
We know this Y value would be
2.7.
okay. So let's just use 3.
So we're approximating E to approximate.
I'm confused. That sounds like cheating.
How are you approaching like?
Our
Is 2.7.
fifth derivative
We don't know that.
is E to the X.
We don't know that E
But
equals
it is-
2.7, so we have
But
to
it does
approximate
equal
E
2.7.
because it's 2.7 to
I know.
Yeah,
But we don't have our calculator to help us with that calculation. Do
But
you
you know
see
it
this
now.
right here?
No calculation.
Do you want to take 2.7 and divide it by 5 factorial and give me a number out of that? Was that your calculator? Because I don't. Okay. So we know that our remainder is going to be less than, we're overshooting it by a little because we're rounding, 3 over 5 factorial times 1 to the 5th.
What's 5 factorial? 20?
Yeah.
So it's 1/4. No.
Right in.
1/40.
This is kind of alright. Part B.
So e to the first would live in the interval. I'll do common denominators for you.
Thank you.
I want to make sure we get through our lesson.
So, well, we already know what E to the first is.
So this is,
I don't understand. Is this just like a practice problem that we would actually use for?
so I know you know what e is,
Yeah.
okay? But this is for you to actually see what's happening, okay? They're easy derivatives, so it's a short problem, right? The calculations aren't bad, okay? It's more to just practice. I know that we can figure out what e is off the top of our heads. Okay. Polynomially, we could approximate it with a pretty close to what it would actually be. Okay, read through the example number 4, please. We have until 35.
Brain break.
It gives you f of 2, f prime of 2, f double prime of 2, and f triple prime of 2.
We just add them all together.
I would not do that.
Alright.
But our function is approximately the polynomial of the function value plus our first derivative times x minus a plus the second derivative over 2 factorial times x minus a squared plus the third derivative over 3 factorial times x minus a cubed. Okay, we can use all of our derivative values to write our polynomial without even knowing what the function is.
Very cool.
All right, so with your calculators,
Got it out.
we want to approximate the function at 2.3, which means plug 2.3 into your polynomial. Now, let's think ahead. What is 2.3 minus 2 every time?
0.3.
Okay, so when you plug this into your calculator, you know that the parentheses are going to be 0.3. Okay.
Is there a shortcut for factorial?
Yes?
It's still the alpha of F2, whatever. When
Alpha F29.
Yeah.
It's so I'm
You have to think it's weird how that works.
It's
What'd you get, Chris?
6.29.
I can confirm.
I didn't get that.
I got
Why?
6.9.
I got 6.9 too.
Yeah.
Yeah, I got
Is that what your calculator says? 6.29.
Nope.
So you didn't actually plug it in.
My calculator's almost dead and I didn't realize that.
But we're approximating, so it's close enough.
It's okay. I live in something.
Okay.
So it's fine.
So we want the Lagrange error bound. So our error, you don't want to write R, is of the form, okay, this is a third degree polynomial, right?
Yep.
So we need to use the max fourth derivative over 4 factorial times,
Why is there 0 minus 1?
What's the if power to? What is that?
Oh, it's
But is that an M after the M?
4.
That's a 4? Okay.
Yes, sorry. Okay, and then we have x minus c to the 4th. This is what we're approximating. This is where it's centered. Okay. Well, what is our max derivative?
Yep.
We know it's less than or equal to 9. Okay. So what's the error to 3 decimal places?
Wait, how do we know our max derivatives? Oh.
They give you no information about the function. They have to give you that.
Yeah.
What do we get? Okay, we get 0.003. Thank you for helping me.
That's exactly what I was about to say.
Okay. Could f of 2.3 equal 6.992?
No.
Nope.
Yeah, I don't
Nope.
know.
No.
Too big.
No factorial.
Okay. I have some problems for you. Worksheet that you're going to have to do on a separate sheet of paper because there's no way to do one.
That sounds like a challenge.
If you want to like squeeze it on the back, I have no problem with that. But I don't know if squeezing it on the front's a good idea.
No, it's okay.
You already left. I've done what I wanted out of the show.
My name is just Gus.
I got it.
I'll take that one. You can have this one.
Did you
You guys were all worried about getting done in time and like packing up while I was still talking. We still have 2 minutes left.
Two, that's it.